So in this part of the unit, we're going to be talking about the energy in chemical reactions. And one way we can look at it is through something called a reaction energy diagram, which is what you're looking at here. This is our reaction energy diagram for the reaction A plus B gives us C plus D.
So, I mean, I think I know some of this stuff. Like, I have A plus B right here, that this side is my reactants of my equation. So could I then there assume that over here, that on this side, that this is going to be my energy of my reactants?
And that makes sense because, I mean, we read a graph left to right, so we should start out with reactants.
Yeah.
So then what do we call the things we end up with?
Okay, so over here, since I have C and D, and then C and D is my products, that this would be the, energy of my products over here.
Yeah, so the reactions of the products we're pretty familiar with. What we're not really used to is what's happening there in the middle, because we're usually just mixing things together and all of a sudden we have products. That middle part is what's called the activation energy. It's always going to take some kind of energy to make a chemical reaction happen. So that big hump in the middle tells us how much that is. That's our activation energy.
Okay, so you said it's the big hump in the middle. So if it's my activation energy, that would be like the energy that I started with. So this would be all the way across here. All the way to the very top of this as well.
Yep, all of that energy required to go from where you're starting out to the highest energy point, that's your activation energy.
All right, so I'm going to abbreviate this to be ACT E, but that's what that means, guys, is activation energy.
And we'll talk a little bit more about that at the end of the video. So the other thing we can figure out is we can figure out what's called the delta H, the change in enthalpy for our reaction. And it sounds kind of scary, but
enthalpy. Whoa, that sounds like a... Okay, explain to me that word again.
Enthalpy is a fancy way of saying heat, really. And actually, most of the time when we're talking about enthalpy, that's where we see our delta H there.
Okay.
That's just the change in energy, the change in heat from over the course of the reaction. So all we do to find that is take the energy of our products, which was C plus D.
All right, so the energy of our products would be right here, so I'd run over, and I know that my energy of my products would be 20. Okay.
Minus the energy of our reactants, which is
40, because you said it was right here.
And so we've got 20 minus 40.
Ooh, dicey. Negative 20.
It's going to be negative 20. If you notice on our axis, it says kilojoules. So our units on this are going to be kilojoules.
Okay.
That is the delta H for our reaction. It means that our products are at a lower energy than our reactants were. We've given off energy. And so if you think back to when you were in middle school, what if things are giving off energy, how are they going to feel?
They're going to feel hot.
They're going to feel hot. And if we had reactions that felt hot, what did we call them?
Is it kind of like when something's exiting? So I'd call it like a exoskeleton's on the outside, heat's on the outside, so it's a exo and thermic?
Exothermic.
Oh,
so since we're giving off heat to get these products, it's an exothermic reaction. So anytime you've got a negative delta H, that's going to tell you have an exothermic reaction because you're giving heat away. Think about it like your bank account. If you give money away to somebody, what happens to your bank account balance?
Oh, we're going to be in the red and, yeah, negative numbers.
So, yeah, you're taking away money. So it's an exothermic reaction. You're giving it away.
Okay, so did I really actually have to do all this math just to see that my products are lower in energy than my reactants?
You really don't. And anytime you look at a graph and you see that your reactants are higher up than your products are, you know this shape of the graph has to tell you that it's an exothermic reaction.
Okay.
All right, so let's look at another one. And this one, we're going to have you try on your own. So pause for a second. Try to label the energy of the reactants, the energy of the products, and the activation energy on this graph, as well as finding your delta H. So come back when you've got that done.
All right, so we said the energy of the reactants. Reactants is what starts the reaction, so that's what's going to start the graph. So I'm going to put an E for my energy of my reactants. And then our products are what ends. So that's going to be the end of the graph. So this we're going to write the E, and big capitalized E is for energy, guys, in case you haven't picked that up, of our products.
And actually, we could skip ahead a little bit if we wanted to, because one of the things we asked you to find is this endothermic or exothermic. So our reactants are lower in energy than our products are. So is it going to have to give away energy to get there or take in energy to get there?
Take in energy.
It's going to have to take in energy, which means it's what kind of reaction?
Well, I'm saying in a lot, so I would say endothermic.
Endothermic. And we'll see if our math supports that here in a minute.
Okay, so if it was an endothermic reaction, we would, if it was exo, it was a minus H. So if it's endothermic, it's going to be a positive delta H, if we're right, correct? Okay. So we have one last thing, and that is our activation energy. So remember, activation energy is where we start to the very highest point. So this whole entire thing right here is our activation energy. Okay.
Okay? And so now we want to find our delta H and see if we were right on our prediction about endothermic versus exothermic.
Okay, so for delta H, we had to do our products minus our reactants, right? So our products we run across, and we're getting 100. These are nice, easy numbers. Minus our reactants, run this across again, and we're getting 50. 100 minus 50. Man, do I need to get my calculator out for this?
Hope not.
50.
Yep. And if you look again, over at your y-axis, your units are going to be kilojoules.
Thank you, thank you.
All right. So is that a positive number?
It is a positive number.
So does that support what we thought, that it was going to be an endothermic reaction?
Yes, it does. Man, you know what's kind of weird? I was thinking about this. You're saying endothermic and exothermic, and we're going to go ahead and erase this real quick. If you look at this, to me, it kind of looks like this graph stays up in the hump right here. So it's like I'm still in my little hump area. Whereas if I go back to the other one that we just looked at, and we said it was exothermic, and I go ahead and I erase this so it makes a little bit more sense. And we look at our hump right here, it's exiting out of the hump.
Okay.
So that might be another way to help you, maybe not. So
something to think about. All right, so the last thing we wanted to talk about, I promised we'd talk a little bit more about activation energy. What the activation energy can tell us is a little bit about how fast things are going to go. And you can think about that actually by just thinking about the shapes of your graph. If you're trying to climb a really, really steep hill, are you going to be able to do it really fast?
no.
So the steeper your graph, the higher your activation energy, the slower the reaction tends to go. So over on this first one, what was our activation energy? We said it was from our lowest point to where?
To the very, very highest point.
And so what's our total activation energy?
All right, so we went from 50 to 250. So it took a total to get from here to here of 200 kilojoules of energy.
Okay, let's compare it to our other reaction. We started out at...
So we started at 40, and then we went all the way up to 100. So 100 minus 40 is 60 kilojoules.
So which one of those things do you think is going to be harder? The one that takes 200 kilojoules or the one that takes 60 kilojoules?
200 kilojoules. That mountain looks really steep.
So which one's going to be faster?
The shorter one. Okay, so that would mean that this graph over here would be my fastest reaction because my activation energy is lower.
Right. So that makes a lot of sense. If it takes less energy, it should go faster. Now the other thing, you should remember a little about catalysts. You called them enzymes back in biology.
Man, I thought this sounded familiar.
What did enzymes do for us in chemical reactions?
They made things go faster.
They made things go faster. And we just said that activation energy and how fast things go are tied together. So what our catalysts do for us is they actually lower our activation energy.
So would that be like saying that you would come in here and if I added a catalyst to this reaction, it would go up, 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 but then my hump would be like right there instead?
Right. So it makes your graph a lot shorter, which makes the reaction go faster because it's a lower activation energy. Make sense?
Makes sense. Okay, so what does a catalyst do to the activation energy? It, lowers the activation energy.
And makes the whole reaction go faster.
Whoops.
All right, so you can move on to your second video, which is talking more about how we can calculate our delta H for our reactions. If you're running into issues, let your teacher know.
All right. Bye.